Hi, Math 2 Enhanced. So this is notes for solving log equations. So first of all, let's talk about ways to solve our equation when it's in exponential form. Example 1 and 2 on this page give you an example of an equation that's in exponential form. Notice on both example 1 and 2, my exponent contains my variable x. So I'm going to want to get my exponent down out of being the exponent so I can get to my x. So one method that works sometimes, and when it does work, it's generally very efficient, is to try writing both sides with the same base. So for example, if I can write something, the base b to the x power is equal to the base b to the fourth power, then I can conclude that x has to be equal to 4. If I raise the same base to each of those exponents and they're equivalent, then the exponents must be equal. So let's look at an example of that with example 1. So I have 3 to the 2x and 27. And the moment I look at that, I think to myself, oh, well, 27 is 3 cubed. So I could write this equation as 3 to the 2x equals 3 cubed. So the nice thing about that is that I can now see that clearly 2x and 3 must be equivalent. Now keep in mind, you are not getting rid of the 3's. You are not dividing the 3's away. You're not canceling the 3's. I'm going to write a totally new and separate equation setting my exponents equal to each other. And now I'm going to solve this. I'm going to solve by dividing both sides by 2 and getting x equals 3/2. If I want to check my answer, I could plug it back in. Let's see what happens when I check this. So I'm going to plug my 3/2 in for x into the original equation. I'm going to see if that's equal to 27. Well, the 2's cancel, and so my exponent would just be 3. And so 3 cubed does equal 27. I feel great about my answer, and I would move on. So what about problems where I can't get like bases, or even if I can get like bases, if it's not very desirable? So this second method, this second method always works, but the algebra can get very cumbersome at times. So that's why the same base method is very helpful. So first of all, I'm going to take the log of both sides, logarithm of both sides, and then I'm going to use my power rule to move exponent. So let's see what that looks like. So I have my b to the x, let's say, equals a. So I'm now going to take the log of both sides. Remember, you can do that as long as you do it to both sides. I want to keep my equation equivalent. So when I do this, when I've taken the log of both sides, I can drop that x, which is my exponent, down in front using my power rule. So this becomes x times log of b equals log of a. Keep in mind that my logs are just numbers. So I'm simply going to divide both sides by log of b, and that allows me to get what x is equal to. It's equal to log a divided by log b. So let's look at an example of that with example 2. Example 2 I really couldn't do with same base method. So I'm going to take the log of both sides. So I'm going to do log of 2 to the 3x equals log of 15. Now that I've done that, I can move my 3x down in front with my power rule. So I get 3x log 2 equals log 2 equals log 15. Now remember, log 2 is just a number. So I'm going to divide both sides by the log of 2. And when I do that, I get 3x equals log of 15 over the log of 2. So next, most of the time my students know, hey, I want to divide both sides by 3. Sometimes students get confused on the right side because they see like a triplex and they're not sure what they have here. But remember, really, when you divide by the 3, it's just in the denominator. So I will say that this is the same thing as log of 15 divided by 3 times log of 2 in the denominator. So this is what I want to put in my calculator. This is the better way, and if you were in the classroom, we talked about common mistakes kids make. But if I were you, on my calculator, I would type log 15, divide by log 2, divide by 3. Divide by everything in the denominator. You could use some parentheses and multiply the denominator, but I just think that's a better way to do it. But you need to visualize it as a numerator denominator. There's never 3 levels. We don't have a triplex here. We just have a numerator and a denominator, and that 3 is in the denominator, and we divide by the numbers in the denominator. When I do that, I get approximately 1.302. If I want to check that, I can plug that back in. So I'm going to go back to my original. 2 times the 3 times 1.302. And it should be approximately equal to 15. I say approximately because I did have to truncate around, so it may not be exactly, but I would get something pretty close to 15 when I do my check on my calculator. So how about if it's set up with a logarithm? So if it's set up with a logarithm, I've got 3 different ways I might go about simplifying it. So first of all is when I have just one log on one side. And I'm just going to use my backwards C method here. I'm going to use my backwards C to rewrite it as something exponential. So let's start at my base, go across my equal sign, and finish at my x. So I'm going to write 3 squared equals x. And at this point, you would do whatever your math says. And in this problem, it's particularly easy. My x equals 9. So what happens if I have more than one log? In fact, I have a log on both sides. So let's think about this. If log base b of some x is equal to log base b of some y, then I know that my x has to be equal to my y. It would just make sense. If it's the same log and same base and they're equivalent, then the x and y must be equivalent. So in number 4, notice I have log base 10 on both sides. This is a log equals a log. And if they really are equivalent, then my x minus 2 must be equal to 5. Please take note, I did not divide by or cancel the log. I did not divide or cancel the log. I just rewrote the 2 arguments, x minus 2 and 5 equal to each other. I'll add 2 over and get x equals 7. So let's take a look at example 5. This also has a log base 2 on both sides. So I know then my 2 sides must be equal to each other. So I am now going to add x over and get 8x. And I'm going to subtract 1 over and get 1. And I'm going to divide by 8 and get x equals 1/8. And I need to make sure, going back to example 4 too, and both 4 and 5. I need to check for extraneous answers. I believe it does say this at the top of our notes. I don't want to get a negative inside my log. So on number 4, I would take this 7 and plug it back in. And in my head, I'm seeing 7 minus 2 on the left side, which is a positive number. I'm not going to worry about it. I'm just going to move on. Number 5, I'm going to plug in that 1/8. And I would get 7 times 1/8 plus 1, which would be a positive number on the left that's inside the log. And on the right, I would do 2 minus 1/8, which is 1 and 7/8. Again, a positive number. I'm just mentally looking back at my original equation and making sure that my answer doesn't make either argument negative. So let's jump down and look at the next 2. So the next 2 problems have multiple logs in them, And so I'm going to use my quotient rule and product rules to simplify them to the above situations. Either a log equals a log, or a log on one side, and I can use my backward C. So let's take a look at example 5. Example 5 is 3 equals log 8 plus 3 log x. That plus sign is making me think of the product rule. And this 3 out in front makes me think of the power rule. Remember, I'm trying to condense to a single logarithm. So I'm condensing. I'm doing my condensing moves. So this is really 3 equals log of 8 plus log of x cubed. Since it's a plus sign, I know I can rewrite this as 1 log, and this log would be 8 times x cubed. Now, I'm very much like up above, I have a single log. So I'm going to simplify this by doing my backward C. It might help you to visualize this better if your log of 8x cubed was on the left and the 3 was on the right, but it makes no difference. And think back, when I don't have a base, I'm going to include a base of 10. So now I'm going to do my backward C, and I get 10 cubed equals 8x cubed. Doing your algebra here, you have a couple options. First of all, you could do a cube root of everything right now if you wanted to. But I'm going to I'm going to do 10 cubed, which is 1,000, equals 8x cubed. I'm now going to divide both sides by 8. I'm trying to isolate my x term. And I get 125 equals x cubed. And finally, to solve this, I'm going to take the cubed root of both sides. And I'm going to get 5 equals x. And I can see that if I plugged a 5 back in, it would not make, obviously it's a positive 5, it would not make either one of my logs negative. It's a great answer. I would move on to my next problem. So let's say you want to check this one. Let me change to green. If you wanted to check this problem, you could plug the 5 in for x, and you would have 3 equals log of 8 plus 3 log of 5. I would just use my calculator. I would do log of 8 plus 3 times log of 5, and I would see that I would get an answer of 3 for it. And then I would know that I did definitely get the right answer. So this next problem has some different ways you can finish it. But to begin this problem, I'm going to notice the minus sign. I also notice the coefficient of 2. So one way I could use this is using my quotient property because of the minus sign, and also my power property to put the 2 back on top. This becomes log of x squared minus log of 4 equals 0. So one method I could do is to do the quotient rule. Because of this minus sign, I could write a single log with x squared over 4 equal to 0. So this is me condensing and writing it as a single log. So now I could use my backward C. I do need to put a 10 in for my base. I could do my backward C, and I get 10 to the 0 equals x squared over 4. 10 to the 0 is 1 equals x squared over 4. I can now multiply both sides by 4. I get 4 equals x squared. To solve this, I'm going to take the square root of both sides. Now remember, this became a quadratic equation. So the moment I take the square root of the 4, I want both my plus and minus answers, which would be plus and minus 2. So let's talk about that plus and minus 2. This is x equals 2, and it's also x equals negative 2. Sometimes both answers won't work, or neither answer might work. So let's take a look at this. If I plug 2 in up above, I would have 2 log 2 minus log 4. That's great. None of my logs went negative. However, when I plug in my negative 2, I'm looking at 2 log of negative 2 minus log of 4 equals 0. Unfortunately, this log of negative 2 right here is going to give me an error. You can always do it on your calculator, but I never want to take the log of a negative number. So actually in this problem, I'm not going to keep the negative 2. I'm only going to keep the solution of 2. I do want to back up and discuss one other way to do this problem. Since this problem was equal to 0 and not another number, I could have added the log 4 over to the other side. I would have had log of x squared equals log of 4. This is, instead of the backward C, this is a log equals a log. So I can simply set the x squared equal to the 4, and I can work out and get the exact same answers. So let's look at some problems in that 1/8. Oh, sorry, next page. These problems get a little tricky quite quickly. So first of all, let's look at number 1. Number 1 is not a problem I can do with the like bases method. There's no base, or there's no exponent I can raise 5 to get my 20. So I'm going to take the log of both sides. So I'm going to take the log of 5 to the 2x and set it equal to the log of 20. This does allow me to drop the 2x in front, and I get 2x log 5 equals log 20. I'm now going to divide both sides by log 5, and I get 2x equals log 20 divided by log 5. Now I'm not done yet. I now also need to divide both sides by 2. When I do that, my 2 is really in my denominator here when I divide both sides by 2. So, but when I type this into my calculator, let me get a different color. I would recommend that you do type in log of 20, that you divide by log of 5, and that you also divide by then 2. If it's in the denominator, you divide by it. If it's in the numerator, we multiply it. So log 20 divide by log 5 divide by log 2. Again, if you're having a calculator issue, please come in to see me. However, there's really only ever a numerator denominator. That's why I wrote the 2 times log 5 in the denominator. When you do that, you should get approximately 0.9307. So you can check your answer. So now let's jump over and look at the second one. In this problem, again, I can't very easily write the 12 and 15 to the same base. So I'm going to take the log of both sides. And when I do that, I'm allowed to write my exponent out in front. When I do that, I'm going to put parentheses around my exponent so that I keep the 2x minus 8 together. And I have my log of 12 equals my log of 15. I'm now going to divide both sides by the log of 12. And I'm going to get 2x minus 8 equals log of 15 divided by the log of 12. I'm now going to add 8 to both sides. So now be careful. You are adding 8 to my quotient. So you have to do log of 15 divided by log of 12 first on your calculator, and then you have to add the 8. And last, I'm going to divide both sides by 2, and I'm going to get that x equals, and when you type this in your calculator, let me grab my highlighter here so I don't mess anything up too much. You have to do the log of 15 divided by log of 12 first. Then you're going to hit equals. You're going to add 8. You're going to hit equals. And then you're going to divide by 2. You have to do all that in the correct sequence so you can get the correct answer, which should be something around 4.5449. And you can truncate around however you'd like, but be very careful on your calculator there. So number 3 can be done by taking the log of both sides, but it also can be done with like bases. That 2 and not 4 makes me think of 2 squared being 4. So I'm going to write this as 2 to the x plus 6 equals 2 squared. Because now I can see I'm not canceling my 2's. I'm not dividing my 2's away. I'm going to rewrite a totally new equation by setting my x plus 6 equal to my 2. My exponents must be equal to each other in order for that equation to be true. And so then I'll subtract x over, and I get x equals negative 4. I can always check my answer by plugging it back into the original. So let me put a box around my first 2 answers here. So let's take a look at number 4. Number 4 can be done, of course you can take the log of both sides, but I really recommend that you think of like bases, because 16 is really 2 to the 4th, and 64 is simply 2 to the 6th. Our work is much simpler if you do it in exponential form rather than logarithm. If you want to talk about how to take the log of both sides and do your math correctly, please feel free to bring it to class. But it is a very difficult problem if you're going to take the log of both sides. So let's think of the 16 as 2 to the 4th, and that's all to the 5x. Let's think of the 64 as 2 to the 6th, and that's all to the x plus 7. Now I'm going to use my power rule. I'm going to multiply my exponents. So I get 2 to the 20x equals 2. Now be careful. Make sure you distribute here. This is 6 times x plus 7. Let me do one more extra line and write it out. It's 6 times x plus 7, not 6 times x. It's the exponents get multiplied. It's a distribution property. So it's really 2 to the 20x equals 2 to the 6x plus 42. So now, again, you are not dividing by 2. You're not canceling the 2's. But if this is true, if this equation is true, I know my exponents must be equal. So I know my 20x is equal to 6x plus 42. I would subtract the 6x over. I would get 14x equals 42. And then I would divide both sides by 14, and I get x equals 3. So number 5 is another problem that I really would recommend you not take the log of both sides. The algebra is really quite long. I think this problem is done much more efficiently by using like bases, because 243 is simply 3 to the 5th, and 81 is 3 to the 4th. So this is really 3 to the 5th to the 0.2x, and 81 is really 3 to the 4th to the x plus 5. And I'm going to put parentheses around it because I really need to think of the x plus 5 together. So when I multiply my exponents, I get 3 to the x. I believe 5 times 0.2 is just 1. And then over here, I get 3, and when I distribute my 4 to the 4x plus 20. So now I'm going to set my exponents equal. So again, I'm not canceling the 3's. I'm not dividing by the 3's. I just know that my exponents must be equal to each other. So x equals 4x plus 20. I could subtract my 4x over. I get negative 3x equals 20. I'm going to divide both sides by my negative 3. I get 20 over negative 3. When I do that on my calculator, I get approximately negative 6.67. If I want to check my answer, I'm going to go plug that in to my x up above and do my math, and I would see that I get the same number on both sides. If you're having trouble substituting it in, if you're making a calculator error, just stop by and we'll take a look at it. Now, number 6, again, is another problem I really recommend like bases. It's done quite efficiently. The 25 is 5 squared. The 125 is 5 cubed. So I'm going to think of 25 is 5 squared, and I'm going to multiply by my exponent that was already there, and that was 2x. I'm going to think about my 125 as 5 cubed, and then that's times the exponent that was already there of x minus 2. So this is really 5 to the 2x equals 5 to the 3x minus 6 when I distribute that 3. So again, I'm not canceling the 5's or getting rid of them. I'm just realizing that my exponents must be equivalent. And I write 2x equals 3x minus 6. I subtract 3x from both sides. I get negative x equals negative 6. I multiply both sides by negative 1, and I get x equals 6. And again, you can substitute that in up above. You can check to see that 25 to the 6th is indeed equal to 125 to the 4th power, and that's how you can check your answer. So let's take a look at the next 3. I wouldn't recommend doing the log of both sides. I would recommend doing like bases. I will do 7 with like bases to show you how efficient it is. And I'll do 8 because they're very similar problems. I'll do 8 by taking the log of both sides to show you how much like extra work that is, although both methods are fine. So number 7, I'm going to use 2 as my like base. So I'm going to write both sides to a 2. On the left side, I have a 1/2. If I want to put the 2 in the numerator, I'm going to raise it to a -1. So that's 2 to the -1. And I already had an exponent of x there. And 16 is 2 to the 4th. And I already had an exponent of 2 there. So this becomes 2 to the -x equals 2 to the 8th. So now I'm going to set my exponents equal to each other. -x equals 8. Please don't say you cancel the 2's. You didn't. You just rewrote the exponents equal to each other. I'm going to divide the negative over, and x equals -8. So let's take a look at this problem. Again, I would not recommend taking the log of both sides here because you can do like bases. If I could just write down real quick, 32 would be 2 to the -5. And 64 is just 2 to the 6th. This problem goes really quickly if you do like bases. I believe your answer is like -0.6, and it goes really fast. But let's do this as taking the log of both sides just to show you that way. Oh, sorry, I went too far. So I'm going to take the log of both sides, the log of 1/32 to the 2x equals the log of 64. So I'm going to drop that 2x down in front. That's the whole point of taking the log of both sides. So now I'm going to divide my log of 1/32 over. So I'm going to divide both sides by log of 1/32. And they cancel, and I get 2x equals log of 64 over log of 1/32. And lastly, I'm going to divide both sides by 2. But remember, when I divide by 2, it's really in the denominator. However, when I type it into the calculator, I do recommend, let me grab a blue marker. I do recommend that you do your log of 62, divide by log of 1/32, divide by 2. That is exactly what I type in the calculator, and hit equals. And if you've typed it in the calculator correctly, you should get -0.6. So if you haven't got that, bring in your calculator into office hours or before class, and let's take a look and see like what key you're hitting at the wrong time. Okay, you guys. So the last problem, again, I think goes very quickly with like bases. 27 is a great base because 27 to a -1 is 1/27. That's to the x minus 6 equals 27. So now I'm going to multiply my exponents, and I get 27. I'm going to distribute that -1. It's -x plus 6 equals 27. This 27 on the right side is really to the first power. So I'm not canceling my 27s. I'm not getting rid of my 27s. I'm just going to set my exponents equal to each other. And I get -x plus 6 equals 1. I'm going to subtract 6 over. I get -x equals -5. Divide by my negative, and I should get x equals 5. And you can, again, plug that 5 back in and see that. And when I go to check it, let me get my red marker. When I plug that 5 in, I get 1/27 to the -1. I'm trying to see if that's 27. And 1/27 to the -1 would take it from the denominator to the numerator. It does work out. It's great. I love my answer. So let's take a look at number 10. There are a couple ways to think about 10 and 11. So I'm going to do one way, and I'm going to do one the other way. So first of all, it is a single log. If you want to start by doing your backwards C, that's a great idea. So I'm going to start at the 4, go across the 20, and I'm going to end at the 5, the x to the 5th. So I get 4 to the 20 equals x to the 5th. You could do 4 to the 20th power. It's a huge number in scientific notation, so I wouldn't recommend it. But I know that I have to take the 5th root. I have to take the 5th root of this to get x by itself. So now I would grab out my calculator. Now I would do 4 to the 20th, hit equals, and then I would do the 5th root and hit equals. And you should get 256. If you're not getting that number, again, come by with your calculator. Let's talk about how to do something to the 20th, and let's talk about how to do the 5th root on that particular calculator. Now, another thing you could do, instead of the backward C, you could also start by doing the power property. You could drop that 6 down in front, for instance, and you have log base 3 of x equals 12. Now, I can't do a backward C because my log is not isolated, but I could divide the whole thing by 6. And now I have log base 3 of x equals 2. And when I do my backward C, I get 3 squared equals x. I square my 3, and I find that my x equals 9. So that's another way that you could do this problem. So let's take a look at number 12. Number 12 is the problem that I do recommend you drop your 3 down in front. I do think if you did that, your number on the left gets smaller, or your number on the right gets smaller, because I'm going to divide both sides by 3. And I get log base 4 of x minus 6 equals 2. So now when I do my backward C, because I have a single log, I get 4 squared equals x minus 6. That's 16 equals x minus 6. I would add 6 to both sides, and I get x equals 22. What does it look like? Let me get a different color, and let me move this over a little bit for just a moment. What does it look like if you start with the backward C? So if I could redo this one, log base 4 of x minus 6 cubed equals 6. So if I did the backward C, I would get 4 to the 6th equals x minus 6 cubed. And then I would take the cubed root of both sides to cancel it being cubed. And so the cubed root and the exponent of 3 would cancel to x minus 6 on the right. And on the left, give me a moment here, I would do 4 to the 6th, and then I would do the cubed root of that. And it looks like I'm getting 16. And then I would add 6 over, and I get 22 equals x. So both methods work pretty efficiently. Okay, so let's move back here and move on to 13. So 13, I notice I have subtraction. So I'm going to use my quotient rule to write log of x divided by 10 equals 14. So now I'm going to do my backward C, but in order to do my backward C, I need to put my base of 10 in. I do my backward C, and I get 10 to the 14th. Well, that's another crazy number. Equals x over 10. So to solve for x, I need to multiply both sides by 10. Personally, 10 to the 1st by 10 times 10 to the 14th is just 10 to the 15th equals x. I would leave it like this. If you want to do 10 to the 15th on your calculator, you can, but that's a lot of zeros that you're going to be writing. So let's take a look at number 14. There's a plus sign in between these, so I'm going to use my product rule. So I'm going to write a single log, and I'm going to write 5x instead of x5. It's 5 times x. Because of the plus sign, I'm going to multiply my arguments equals 2. Again, I'm going to insert a 10 for my base since there's not a base there. I'm going to do my backward C, and I get 10 squared equals 5x. That's 100 equals 5x. I'm going to divide both sides by 5, and I'm going to get x equals 20. Now, I neglected to mention, I really should be mentally plugging this back in to make sure I don't get a negative log. But obviously, if I plug it in for x, I get log of 20. 20 is not negative. It's just fine. I'm not too concerned about it. So let's take a look at 15. This example has a log on both sides. This is where the logs don't cancel. I don't divide by log. I don't get rid of log. But I know if these two logs are equal, then my arguments must be equal. So I'm going to rewrite a separate new equation. X plus 9 equals 2x minus 7. So I'm going to subtract my x over, and I get x. I'm going to add my 7 over, and it looks like I get x equals, I'm going to add my 7 over, and when I add 7 over, it looks like I get x equals 16 for my answer on this problem. Again, mentally plug that back in, but I'd be doing the log of a positive 25. I'd get another log of 25. So I know that I know that my answer is equal, or I know that my answer is great because it checks out and I don't have a negative log. So let's take a look at number 16. There are 2 logs here, and they are separated by a minus sign. So I'm going to use my quotient rule and write this as log of x plus 4 divided by 6. I know I'm going to divide by the 6 because that's the log that was being subtracted. I know my base is 10 since it's not there. And since there's a single log, this is a problem where I'm going to do my backward C, starting at my base, going across my equals, and coming back to my argument. So 10 to the first equals x plus 4 over 6. I'm going to start by multiplying both sides by 6. I get 60 equals x plus 4. I'm going to subtract 4 over, and I get 56 equals x. So number 17, and again, mentally, if I plugged that in, I'm getting a log of 60 up above in my original problem. It's not a negative number. I love it. It's a great answer. So number 7 also has a plus sign. In this, just like number 17 has a plus sign just like 14 did. So this is the product rule. So I'm going to write a single log by multiplying x squared times 25. I'm going to write as 25x squared equals 2. Now that I've got it down to a single log, I'm going to do my backward C. So let's put a 10 in here. And I get 10 squared equals 25x squared. That's 100 equals 25x squared. Let's divide both sides by 25, and 4 equals x squared. Let's take the square root of both sides, and I get plus or minus 2 equals x. So I do need to double check, but when I put my 2 back into the original problem, it would be 2 squared, it's fine. And when I put my negative 2 back into the original problem, negative 2 squared would also be positive. I'm not taking the log of a negative number, so I actually like both the negative and the positive answer for that one. So let's take a look at number 18. I have a log on both sides, so that means that my arguments must be equal since these 2 logs are equal. Remember, you're not dividing by log, you're not canceling log. Please don't say that. Instead, I'm going to write a brand new equation. X minus 1 squared equals negative 5 x minus 1. On the left side, we have to remember to write it twice. Some of us missed a problem on the last test because we forgot that x minus 1 squared really means x minus 1 times x minus 1. And that would be x squared minus 2x plus 1. And since this went quadratic, I know that I gotta get everything on one side equal to 0. And I like to move everything to the side where my x squared is positive, which is the left side. So let's add 5x, and we're gonna add 1. So I'm looking at x squared plus 3x plus 2 equals 0. When I do my diamond, I would get 1 and 2. Since my a is 1, I'm going to put those into my parentheses. You would be getting x plus 1 times x plus 2. So now I'm going to set each of those equal to 0, and I get x equals negative 1 and x equals negative 2. And at first, I'm really nervous because negative answers do make us nervous with logs. But when I look up above, if I plugged in a negative 1, I'd still be squaring a negative 2. That's going to be a log of a positive 4. That's fine. And if I put in a negative 2 here, I'm doing negative 1, sorry. When I put in a negative 1 in, I'd be getting a log of a positive 5 minus 1, or I'd be doing log of a positive 4. So it looks to me like the negative 1 checks out just fine. So let me erase my thinking here. And let me check the negative 2. Well, when I plug that in, I'd be getting then negative 3 inside my parentheses. But when I square it, I'd be taking the log of a positive 9. So that'd be okay. And over here, if I plug in a negative 2, I'd be getting a positive 10 minus 1. So again, I'm doing the log of a positive 9, so it's okay. So I like the negative 2 as well. It doesn't make me take the log of a negative number. I hope this was helpful. Thank you so much.